Thank you everyone for attending this week's Steel for Lunch. Today's presentation is going to be by S-Frame and Matt on the P-Delta and Nonlinear Analysis in S-Frame. So thank you for attending, and let's go.
All right, thank you again. Thank you all for joining me today. So this session is going to be kind of an introduction to how you do P-Delta and Nonlinear Analysis in S-Frame. And it's actually a good precursor because we have a training course coming up at the end of this month on this exact same topic that will go into a lot more detail. I think it's over 9 hours. It's online, so you don't obviously have to attend in person. But if you guys are interested, it's free to attend for U of A students. Just register with your U of A email, and I think an email blast has either already been sent out or will be sent out in the coming weeks. I'll have more information on that in just a minute. But essentially what I want to talk about today is P-Delta nonlinear analysis in S-Frame. I'll go over the basics, which some of you may already be familiar with, and then the implementation within S-Frame. So we like to use the term, the world is nonlinear. I should have P-Delta and nonlinear analysis here. And really what we're going to be talking about is the different analysis types that we're going to talk in today's lesson. We're going to look at the basics of P-Delta buckling, and then we're going to look at nonlinear analysis. And we're really only going to scratch the surface. We simply don't have time in one session to discuss all of this. But as I mentioned, we do have a training course that goes into a lot more detail if anyone's interested. I'll then wrap things up at the end with a few questions, a few overview points or summarizing points, and any questions that you guys might have, I'll try to answer then if we don't answer them as we go along. You guys are more than welcome to ask questions, either by typing them or just unmuting yourself and asking them as well. I'm not intending to keep this as a strict formal presentation. It's meant to be open-ended. So why don't we talk a little bit about the different analysis types that are available in S-Frame for those of you that maybe haven't explored what's out there in S-Frame. So we do linear analysis, and here I got a little graph that describes linear and nonlinear, which you're probably familiar with, but it'll just help with some of the explanations a little bit later on. Basically, this is meant to determine the displacements and stresses with a single load based on the initial geometry. So there isn't any deformation as we're applying the loads. It's all based off of the initial geometry and then the post-analysis geometry. So this doesn't take into account second order effects like large deformation, behavior, any nonlinear stiffnesses, P-delta effects, those sorts of things. And the stiffness is assumed to be constant regardless of how much your model deflects. Now with P-Delta analysis, which is one of the topics we're going to be talking about today, in S-Frame we use a rigorous second order P-Delta analysis, which can account for the both big and little P-Delta effects, and we'll talk about that more in a bit, that are required by the direct analysis method, and as well as the new Canadian S1619, I think it's Appendix 0.2 methods as well. Then we have nonlinear analysis. And we'll talk about this as well today. Basically, how this works is the loads are applied incrementally and new geometry is formed and loaded, and then the solver will then perform a series of these analyses with each incremental addition of the loads. So in this situation here, we've broken our load vector up into 4 increments, and we've analyzed 1 increment, and then we've found the geometry based off of the deflections that have happened due to that one load increment being applied, as well as the updated stress stiffness matrix. We then apply the second increment on top of that, onto that updated model with all the updated geometry and stress stiffness matrix, and load that and analyze that. And it's an incremental process that we'll describe again more later on in the presentation. And of course, this takes into account second order effects like the P-delta effects that I mentioned earlier, nonlinear geometry behavior. So that could be large deformations. We have cables that have tension stiffness but no compression stiffness, tension only members, and even nonlinear material behavior as well. We have link elements that can be used to describe that. And these can be applied to other types of analysis. So with P-Delta analysis, we have P-Delta stress vibration. We have P-Delta buckling analysis, which we'll talk about. We have a lot of different nonlinear variants to these different types of analysis as well. And we're not going to go into all of them today, but you can see what's out there if you're curious. And there may be situations where you would want to use these and they would be appropriate for your scenario. We're going to try and perhaps educate you guys in terms of when you might want to choose one over the other. So when would you want to account for second order effects? Well, one of the examples would be if your subject, or your structure, excuse me, isn't very stiff and might be subject to sway. So we get a lot of lateral deformation that could certainly influence the decision to use second order analysis. Also, if when our model deflects and the geometry changes, it will change the stiffness. And a great example of this is cables, like I already mentioned. If a cable is under tension, it's going to have a much different stiffness than if it's not under tension, where it's effectively a zero stiffness element. At least in SRAM, that's what we consider it as. Now, design codes may also describe when you would need to use second order analysis, and that's one that requires perhaps a little bit less judgment on your part since it's spelled out for you in the design codes. Or if you want an accurate analysis, the reality is that the most accurate analysis will be a nonlinear analysis, but it does take longer. It is more, I would say, intensive for the engineer to go through as well. So there are situations where you may have to weigh the accuracy versus the time and processing information requirements that are used in a nonlinear or P-Delta analysis. Now, it's not to say that it's always hard, and the examples we're going to be using today are very simple examples that I think you'll be able to agree don't necessarily equate nonlinear or P-Delta second order effects to additional complexity from your part. Let's start by looking at P-Delta analysis. And this occurs when second order effects will increase the calculated moments or deflections and forces that you would normally experience during a first order analysis. And there's basically two methods for accounting for these effects. We have a second order analysis, which we'll be doing in SRAM. There's also another method that you're probably used to doing by hand, where you approximate these effects by using magnification to basically magnify the first order effects for the second order behavior. And we're really going to be focusing on item number 1 here today. So we'll look at some examples, but we're going to start with the big P-Delta effect, where here we have imagine a beam. It could be a column perhaps as well, where it deflects by a certain amount. We're going to call that amount delta. And if that beam was axially loaded, that axial load, which we'll call F, is now eccentric to the base because of that lateral deformation, which is delta. So now F is eccentric to the base, and we have a moment arm developed there. That wouldn't be accounted for if we were just loading our original geometry. So those deflections from that delta deflection, that's going to induce some additional moments. We call them secondary moments, as the end of the member that's carrying that load is now no longer in line or plumb with the base. So in a P-Delta analysis, this model is resolved with a new stress stiffness matrix, and the secondary effects are then accurately accounted for using this P-Delta analysis. And this is all done in one process within SRAM. And this might illustrate a little bit more. I'm using different conventions for this graphic, so I apologize in advance for not being consistent there. But I think with the diagram, it might help explain things a little bit better. So let's start by looking at the left-hand side. We have our column, and the top of the column here, we're just illustrating with the square, which is our free end. We have a lateral load F and an axial load P. And when things deflect due to the lateral load in F, now P is going to be eccentric to this base, and this is that delta that we were talking about. So how it works basically is SRAM will first analyze the model on the left linearly. And then the structure is going to deflect as we see here. And the stiffness of the structure has been updated as it's deflected. And a second linear static analysis is then performed on the model with the updated stiffness. So this is essentially how a P-delta analysis works. It starts with the linear static analysis to compose to derive the stress stiffness matrix of the deflected shape. It doesn't update your geometry though. And then it runs a second linear static analysis, all within the same run of the analysis, or the solver, on that updated stiffness model. And in this scenario, this is illustrating the big P-delta effect, where we have, again, a tip deformation, but this is also true for the little P-delta effect. And on that topic here, let's look at an example of the little P-delta effect. Rather than having one end be free and the other one be fixed, now we can see this would be more of like both ends, like a simply supported beam, for example. So this is more of a local deformation in the member rather than a structural global deformation, I guess you could say. And this would be maybe more applicable to situations where you have slender columns or maybe large deformations in a model. And both the nonlinear or P-delta analysis will account for this little P-delta effect. So imagine again that we have some sort of axial load on this beam, and then either a moment or perhaps some sort of lateral load pushing this downwards. We induce this deflection, which is little delta, and that's going to induce some additional secondary order effects. In order for us to account for this, though, accurately, we need to be able to have more than one analysis element. And that's not hard to do. It only requires a single analysis, and we'll show you how that's done in the next few examples. Now, we get a lot of people asking about the difference between P-delta and nonlinear analysis, and I'll try to demystify that in this presentation. But basically, the difference here being that for a P-delta analysis, the new geometry is updated, nonlinear analysis, the new geometry is updated for every time step, or every load increment might be a better term. Whereas the P-delta analysis is only going to do this for the update for one iteration. So a P-delta analysis can be thought of as just a single iteration nonlinear analysis, and you'll get very similar results between the two. And if you wanted to run a nonlinear analysis to account for these little or big P-delta effects, you can certainly do that. So now let's try to look at an example here. And I've got this one open on SRAM already. It's a simple 2D frame, although I'm going to be working within the 3D version of SRAM. And we've subdivided this into multiple analysis elements. And we're going to expect to see some sway buckling. So let me just open this up here. This is the model that I'm looking into. And I'm actually going to start with just a single element model. So each basically span between adjacent elements will be a single element. And let's start off by looking at the geometry that we have. So in this model, we've got some arbitrary section properties. I've just defined a single section for the entire model. And if we look at our reactions or supports, we have fully fixed base supports on this model. And I'm just preventing this model from moving out of plane using what we call default constraints. So I'm basically constraining this model from moving in the y-axis. Now, if we look at the loads, we can see here that we have a few different load cases, or a few different loading scenarios here. Basically, I have the combination of a 15 kilonewton load on one end of the model and a 25 kilonewton lateral load. And we should expect there would be some combination of these loads will induce some second order behavior, the P-delta effects that we were talking about earlier. So why don't I go ahead and run a linear static analysis to start. So I'm just going to click Run Analyze, which is either the Run menu, or I could just click this Footsteps button. And I'm going to run a linear static analysis, again, observing the response of my model to those two loading scenarios. Click OK. And it's just running on my other screen here, so I'll drag it over. We can see here again that load case number 1 solved for linear static analysis. I'll pay more attention to this as we go through some other analysis types as well. But really what I want to illustrate here and maybe highlight is if we look at the deflection, what sort of deflection am I getting? So for a linear analysis again, I'll toggle off the display of my joint loads. In the x direction, I'm getting about 18.4 millimeters of displacement at the top of my beams. And in terms of moments, we can see here the maximum moment we're getting is about 10.9 kilonewton meters. That's the same in the positive and the negative direction. So that gives us a baseline, 18.4 and 10.9 kilonewton meters. Now I'm going to do a different analysis. I'm going to just do a P-Delta static analysis. Just the next one down here. We don't have to change anything else about our model. I'm just going to click OK to analyze this. And you can see here as we go through the solution trail for the P-Delta static analysis, what happens first is the solver is actually going to do a linear static analysis. Again, what it's doing is it's determining the stress stiffness matrix based off of the stress model that we've already analyzed. And it's using that updated stress stiffness matrix and performing a second P-Delta or linear static analysis on that. And this way we have basically two different analyses showing up here. And now if I look at the results for the exact same loading, the exact same geometry, I just want to compare the differences. So I'll look at the deflection again. And right away we can see that we're getting about 0.8 millimeters more deflection here on the top of the beam. And for the moments, we're getting here, I think we had about 0.5 kilonewton meters more moment for our maximum moments. And that's clearly an indication that the P-Delta effects or the second order behavior maybe isn't significant, but does play a role. I guess the definition of significant will vary from person to person. Now what I'm going to do is I'm going to try increasing the number of analysis elements that I have. So I'm just going to go to the edit menu, and without changing anything else, I can just go to subdivide. And this will allow me to add additional nodes to my model without changing the existing properties. So I'm just going to say for the members here, let's break every member into 3 links. I'll click OK. And it's just going to give us a number of nodes along the length of each member that will better represent complex deflected shapes and so on, and also allow us to consider little P-Delta effects that could be occurring. So now I'm going to go analyze, and I'm going to reanalyze for the same analysis type here, but this time I'm just going to have the additional analysis nodes. So click OK. We had a clean solution again. I won't show that once more, but here we can look at the deflections. We can see here that despite the fact that we've added these additional analysis nodes, the deflection amounts haven't really changed, 19.2 millimeters, and then our moments haven't really changed either. So that's probably an indication to me that the little P-Delta effects aren't really a big concern in this situation, more likely going to be the sway effects that we're seeing in the model globally. And we can see that from the deflection diagram. Now, if I go back into my slides here, I actually have a bit of a comparison between these. I was just comparing basically linear static analysis versus P-Delta static analysis, and we can see that we're getting a difference. It's less than 5% for deflection, but you can see that the results do vary between the two models. Despite the fact that the models are identical, the way that we're interpreting the response is different. P-Delta static analysis is considering that updated stress stiffness matrix from the original loading and geometry. We can look at one more example here, where we have, again, a fixed base column and axial and lateral loading. And I'll go through this one a little bit quicker. Just give me 1 second to load it up. So this model, again, isn't too exciting to look at. Basically, we've got a fixed base column. I'm really only concerned about results in one direction, which is the in-plane direction, the XZ plane. We have the same section property assigned. And if I look at our loads, again, we have this load case called P-Delta. Now if I just toggle on the display of my reaction loads, or joint loads rather, I have a 1 kilonewton axial load and a 0.1 kilonewton lateral load at the tip. So again, just to start this off, we'll run a linear static analysis. And by now we should be expecting that we'll get different results between these two, especially since this model is relatively slender. If I look at the section properties, you can see how large this section is when I render the section relative to the length of the member. So with this deflection tool here, I can see that in the lateral direction for this loading, which again is 0.1 kilonewtons out of plane or laterally and 1 kilonewtons in the axial direction, I'm getting 53.6 millimeters. And the moment we're getting is 1 kilonewton meter. Now if I go ahead and analyze this for the linear or P-delta static analysis, we should expect to see a stronger influence from those second order effects. So we're not getting any issues with our analysis, but again, it's going to first of all run a linear static analysis, derive that stress stiffness matrix from the loaded state, and then use that in the second linear static analysis. And based on the relative stiffness of the elements and the loads applied, we should expect that that influence will have quite a big effect. So again, P-delta analysis run here. I'm going to look at the deflection. We can see that we're getting almost 100 millimeters more deflection now, just based on the fact that this model is more prone to these second order effects. And this is not a realistic scenario, but again, just to illustrate the behavior. And so I'm looking at the moment diagrams here. So we can see that we're also getting additional moments due to the eccentricity of that tip. When we're considering that we still have that axial load, it's going to cause additional moments. So for this example, you can see here that it does make quite a big difference when we consider the P-delta effects versus when we don't. Now, before I move on, were there any questions about what we've discussed so far? Okay, I assume that's a good sign. If you guys do have any questions, feel free to type them in the chat pane, or you can always just unmute yourself and ask them whenever you want. I'll do my best to respond. So we're going to turn our attention now to P-delta buckling analysis. And this will help us basically study potential buckling issues in our model. And where we recommend this is if you run a P-delta analysis on your model and you have issues with the analysis, maybe the model is no longer stable, but it was fine for a linear analysis, this can be a sign that buckling might be occurring. And in order to evaluate that assumption, you want to be able to run a P-delta buckling analysis. And the P-delta buckling analysis will determine the critical buckling load of your structure. And what it does is it reports a mode shape and a mode factor, a P-delta buckling mode factor. And if that mode factor is greater than 1, then that means that your structure has buckled according to the associated mode shape under that described loading. And if it's less than 1, then your structure will buckle if that indicated with the indicated mode at the specified loading. So it's going to give you a factor. Let's say that that factor is 2.4. Well, then that's going to indicate that you need to increase those loads by 2.4 times in order to cause that type of buckling mode failure. And because this will use mode shapes and eigenvalue analysis, we do recommend additional analysis elements to really increase the accuracy of your model, especially if you're looking at potentially complex mode shapes, buckling mode shapes. So I'm going to use an example here. It's a P-delta buckling example. And we have a 3D building here. And we're going to say, what happens if our linear static analysis runs, but we receive errors during our P-delta static analysis? Well, oftentimes this is due to buckling. And we want to use P-delta buckling analysis to identify that that's actually the case. And if it does identify that to be the case, we want to drill down into it more and see, okay, well, can we identify a potential weak point in our model that might be isolated buckling in just one specific area? May not always be the case, but it could help us with our evaluation. So let me open up a new model here. And this is a 3D model, so I'm going to look at it in 3D space here. And without going into too much detail here, let me just see, I'll look at the reaction or the supports on our model. You can see here that we have basically pin supports around our structure at the base of the columns. We have some loading, we have some bracing, and I'll just describe those a little bit more. The loading that we have, so we have self-weight loading, we have floor dead loading. Self-weight is an obvious one. It's just going to account for the material mass essentially that we've modeled. For our floor dead loading, it's going to actually use these area load distributions where we have 3.6 kPa on each floor. Floor live, we have 5 kPa. And then we have a wind load case on the wall that's 2 kPa distributed throughout these area load members. And then also a wind west load case with the same magnitude of wind loading, but just on the other wall. And we also have some load combinations. So here we can see that we have load combination. One is just dead and live loads. Then we have dead and wind in one direction and dead and wind in the other direction. So what I'm interested in doing, first of all, is just evaluating the results from this model. So I'm just going to go ahead and run a linear static analysis before I do anything else. So I'll run a linear static analysis for both load cases and combinations. And I just want to see what happens. So when we run through all 5 load cases and all 3 load combinations, we get a clean solution. There are no issues with our analysis. And we can look at the results here. I'll just look at maybe some, I'll just choose one load case or combination at random. And we can look at things like our reaction loads, our deflections, and so on. This is obviously amplified, but you get an idea for how things are behaving. Now let's consider running a P-delta static analysis. Obviously, we have a combination of lateral and axial loads, or gravity loads in this case. So this model does potentially have a situation that we could experience some second order behavior. I'm going to go to P-delta static analysis, again run for both load cases and combinations. I'll click OK. And now we're getting an issue with the analysis. So if I go through this analysis here, we can see that it ran through the linear static analysis of all of these loading scenarios. And then the second order component that comes in is when we get that updated stress stiffness matrix from the first linear static analysis. And we use that updated matrix and apply the same loads to that matrix, that stress model. That's when we're starting to get some issues. We're getting this FYI, LA001 singular matrix. Now this could mean a lot of different things, and it's really dependent on the scenario that you're presented with. So basically what I use this as an indication of is that it's usually an indication of some sort of instability. And because I knew that my analysis ran fine during a linear analysis, but not during a P-delta static analysis where I'm considering these second order effects like buckling and so on, I'm going to check this model to see if there are actually some issues with my buckling analysis on my load combinations, because those are combining the lateral and the gravity load cases. And typically, if something runs fine for a linear analysis, but doesn't run fine for a P-delta static analysis, it's one of those second order effects that's causing the instabilities. So I'm going to go ahead now and I'm going to analyze the model again. So maybe before I do that, I'll just look at some of the results. So let's look at some of the results for the combinations that have lateral and gravity loads. Here you can see that I'm not getting any unusually high deflections from the looks of it, just from a quick scan on my model. But again, some potential buckling issues could still be occurring. Now you can see here I'm getting a little bit higher deflection. I'm getting about 12 millimeters of displacement. But again, I'm going to run a P-Delta analysis or P-Delta buckling analysis to really understand and capture what's going on. So I'll click Analyze. And I'm going to run a P-Delta buckling analysis. So this is closer to the bottom of the list of analysis types, P-Delta buckling. And I've actually already set this up ahead of time, so it's captured that information that I'm looking for. Again, this requires an eigenvalue extraction. So we have different eigenvalue extraction methods here that I won't go into too much details, but you can find more information on our help system. Basically, for any very large model, you probably want to use a subspace iteration method because it will take less time. However, I ran this ahead of time and the Jacobi threshold model works fine for me. I'm also going to choose how many buckling modes I'd like to extract. Now, in most situations, you're only going to be concerned with the very first buckling mode, the one that has the lowest critical buckling threshold. But I have the luxury of looking at more than just that, and it might come in handy sometimes to know the other buckling modes. And then we choose to run a buckling analysis for a specific loading scenario. In this case here, I'm choosing my load combination number 1, which is the buckling dead and live loads. The dead and live load cases. So I'll click OK. I'm going to run the analysis. And you can see here it's running through the linear static analysis for that load combination, as well as the load cases that contribute to it. And it's going to do a sweep. And basically what it's doing is it's iterating on different loading magnitudes of that load combination that I've selected until it finds a scenario that would cause that to buckle, the structure to buckle with those magnitudes. I can click OK here to proceed. And what do I get out of this? Well, I get these different mode shapes. So for my mode shape number 1 here, which is the lowest mode shape, this is indicating to me that for this load combination number 1, which is the dead loads plus the live loads, no lateral loads, I have a factor of 1.299. And what that means is for load combination number 1, I would have to increase the magnitude of that load combination by about 30%, 1.299, in order to cause buckling. And that buckling would occur according to this buckling mode. And if I just use the buckling mode shape tool here, which is the only tool that I really can use in the graphical results window, here I can animate the deflection, or the buckling mode here, and I can see that, well, it seems to be concentrated in these interior columns. So even though I'm not buckling quite with this load combination, I'm about 30%, my critical buckling factor is about 30% greater than the loads applied for this load combination I'm examining. I may still want to investigate this because, that does leave, not a lot of breathing room for what could be a potentially catastrophic event if these were to buckle. But what it does now is it shows me how close I am to buckling, but also where would that buckling be occurring if it did occur. So now I can go into the geometry window and I can say, well, I know these interior columns were the ones that were a problem. Maybe I'll just select my column folder here. And I just want to see, well, is there anything different about those columns than the other ones? Maybe they just have more loads. I mean, they are in the interior. But let's just check, first of all. I go at the member release tool, see if there's maybe different release member end conditions. Also materials. You can see that they're using the same materials here, material number 1. And then finally, sections. So it seems like maybe there isn't any differences between these ones. But at least now I know these are the ones that are going to be closer to the buckling threshold that might be occurring. They're going to be the ones that are kind of governing that potential buckling limit. So I wouldn't want to downsize these columns if that decision were ever have to be made. Again, sometimes this information may not always reveal itself in the same way. But in this scenario, we were able to see, okay, well, we know where, if we were to increase the loads that we have on this model, where that buckling could occur. And that could be valuable to some engineers. All right. I'm actually going to move past this example here. I don't think we'll have time for this one if we want to do the nonlinear analysis options as well. So basically, just for a little bit of background, we modeled a member, a steel member, an I-beam in this case, with a member that has that profile assigned to it, that section property, but we also modeled the exact same thing with shell elements. And we were able to find that the P-delta buckling analysis was able to show us some lateral torsional buckling, given the loading conditions and the support conditions and so on that we had. If anyone wants this model, I can certainly send it along afterwards. We're going to move on to nonlinear analysis now. And as we already mentioned, this is an iterative process, and it is an approximate process, but it will get more accurate with every increment that we add and every iteration that we go through. So essentially what happens is our load vectors are going to be broken into increments. So imagine if we have a 10 kilonewton load and 10 increments, each one of those increments will be 1 kilonewton. And those are going to be applied incrementally. And this will provide the most accurate results of the 3 analysis types that we've discussed today. And it also gives us the ability to consider nonlinear elements, things like tension-only members, compression-only supports, link elements that might describe material nonlinearity, those sorts of things. So we're going to use the same fixed base column example that we were using before to illustrate this. So just imagine here that we have a lateral load that's going to be 10 kilonewtons. And for the sake of consistency, let's assume that we're using 10 load increments for this nonlinear analysis. So what's going to happen first is we're going to apply the first incremental load, which would be 10 kilonewtons divided by 10 load increments. That would be 1 kilonewton. The solver would then iterate until it found a solution. And this process involves, first of all, solving, updating the geometry matrix. So it is going to account for the change in geometry, unlike the P-delta analysis. It's going to update the stiffness matrix like the P-delta analysis does. And it's going to check if it's within a certain tolerance that's specified by the user. If the solution is within that tolerance, then we can move on to the last step. Otherwise, we go through that process, that iteration again. And we specify how many iterations we're allowing the solver to go through in order to come up with a solution within this tolerance. Now, if we get to this stage here and our solution is within this tolerance, we can then proceed to report the unbalanced force, which is basically the error in the solution. Again, it's an approximate solution. And we'd repeat the process again, but using the second incremental load. So we now have 2 kilonewtons on our updated geometry and stiffness matrix. Oh, and I went a little bit too far there. So let's just go through an example again. I'm going to go through an example of a column, just very similar to what we showed for the P-delta analysis, but I think it got some different loads on it. Yeah, just one analysis element. So again, I have fixed base support. And in terms of section properties, I have this wide flange section. You can see here, not quite as slender as that last example. And as far as my loads go, well, I have a few different load cases, and we might not use all of them today. But I have a lateral load that's going to be applied for this load case of 10 kilonewtons, very similar to that magnitude we had before. And I have a unit vertical load of 1 kilonewtons. And I believe I also have some load combinations defined. Yes, I do. So again, this is going to be, we're calling it a P-delta load combination. Basically, we're trying to induce those P-delta effects we talked about earlier. So I have load case number 1, that my lateral load case is going to be contributing with 100% of its magnitude. And I also have this other load case, which I forgot to show you, the 1500 kilonewton load case, which is an axial load, and that's going to be contributing as well. So we have these two contributing with their regular magnitudes. And just for illustration purposes, the 1500 kilonewton compression load is the one that's going to be in that load combination as well. So we're going to compare the different types of analysis, starting with a linear static analysis. I'll run a linear static analysis, and as you guys can probably predict by now, we should expect this to give us the least conservative results. Given the combination of loading that we have in the geometry, I would expect some P-delta effects to be occurring. So we run through the analysis here. We're just running for load combination, number one, which is, again, the 1500 kilonewton axial load and the 10 kilonewton lateral load. And we get a clean solution here. And now if I just look at the results for this P-delta load combination, I get 23.4 millimeters of lateral displacement. And for the moments, I'm getting 50 kilonewtons. And sorry, was there a question there? I heard some audio briefly. If there is, just let me know. Otherwise, I'll assume it was not a question. All right, we'll move on then. And rather than a linear static analysis, we'll move our way down the list to a P-delta static analysis. I'll click OK. We can see here that we're getting a clean solution. I'm not going to describe the process again. We've seen that enough. But if we look at the deflections, not surprisingly, we're getting a lot larger deflection than what we had before. We have a lot of axial load, so there's a lot of stress on this model. And when we induce those lateral loads, it's creating that additional moment that we're having, the column is having a hard time resisting. And here, if we look at the moment diagrams, we're getting about 288 kilonewton meters, so significantly more moment than what we had before. Okay, we're going to repeat this process once again. It's probably getting a little bit repetitive, but again, we're trying to illustrate a point. We look at the nonlinear static analysis now. You can see that we have a lot more options within this analysis than we did for the previous two. We have this convergence criteria, which for most scenarios, I would say there's no need to really change this, but if you have a reason to, I would say go ahead, but maybe just read up on it in the help menu. I'm not going to go into too much detail on this. We have the convergence parameters, so the number of load increments that we have, which in this case here, I'm starting with just one load increment. So that 10 kilonewton load is just going to be broken down into one increment, so it's actually not being broken down, bad term to use. And this is the max number of iterations, basically the amount of times we can go through that iterative solution. So I'm going to click OK to analyze. And here, if we look at the analysis, it's looking a little bit different than before. We have this nonlinear static analysis, the full Newton-Raphson, excuse me, losing my words, method. And it's gone through the analysis of load combination number one. Again, it's just one load increment, and it went through 4 iterations to solve within the tolerance that I forgot to show you. I'll show that in just a second. And it's reporting an unbalanced force that you can see is very small, it's 10 to the negative 14. But what am I trying to see here? Well, if I look at the deflection, first of all, I can see that it's very similar to what we had before. I can say almost identical to what our P-delta analysis had. 158 millimeters and 288 kilonewton meters. And that's to be expected because we have the single increment nonlinear analysis is not really doing the nonlinear analysis justice. It's essentially doing the same thing as a linear static analysis or a P-delta static analysis because it doesn't have those additional increments to update the geometry matrix, which is where it really shines. So now I'm going to go ahead and run an analysis, but I'm going to increase the number of increments. I'm going to say we'll have 10 static load increments. And just so you can see here, this displacement tolerance is the tolerance that we're trying to solve within. So if it reaches this tolerance, then the iterative solution can move on to the next step. So we have 10 load increments now. I'll click OK to analyze again. And this time, we're getting a little bit more detail in our solution trail. So it's going through load combination number one, but you can see there's all 10 load increments shown here. And for most of them, it took 3 or 4 load increments. And you can see here, this is the solution that basically we're left with. We can see here the unbalanced force in each situation and the error in the solution. Once again, we don't have any issues with the analysis. We do have, it's an approximate approach. So when we say unbalanced error, it doesn't mean that there's a problem with our analysis. It's just the approximation that we're using. There is some error built into it. Now I can look at the deflection And I can see now that actually we're breaking this down into more load increments. We're getting a lower deflection, which is interesting. So I'm getting 149 millimeters of displacement and 274 kilonewton meters of moment. And now, again, what's happening is that because we have 10 load increments, we're looking at the results from each load increment, or we have an ability to look at those results as well and update the geometry matrix and the stiffness matrix after each one of those load increments. So we're doing a better job of capturing the results up until the point of that last load increment, whereas the P-Delta analysis is just looking at kind of the start and then at the end. And in this situation here, it's interesting to say we probably need to really break down the analysis results to get an understanding for what's going on, but we're getting about 150 millimeters of displacement. And so what we're getting here is we're getting slightly lower axial loads because some of the deflection is inducing some lateral forces into the model, as this eccentric joint at the top is still being loaded in the vertical direction. The deflection or the angle of that member is going to lead to some lateral forces or some shear forces also being generated as well, as you can see here. This wouldn't happen in the actual, what am I trying to say? The P-Delta static analysis. So that, along with the geometry that we're expecting or that we're getting and updating throughout the analysis, actually leads us to slightly smaller deflections than what we calculated with the P-Delta buckling or static analysis. And we could keep increasing the number of load increments, and eventually we're going to start to notice that the results converge. Despite maybe 10 times more load increments, the analysis will give us a very minor difference in the results. But that point where the results converge will change model to model. So it's difficult to say that for all models you need 10 load increments. I'd encourage you guys, if you have the time, to experiment and look at the results and see where they converge. And one last example here that I want to show for you guys, if I can just bring up the frame here. So I've got a building model very similar to what we've already shown. I don't need to explain it too much, but basically, using all those loads that we saw before, we have some unit live and dead loads. We wanted to look at the scenario where we might have some tension-only bracing in our model, where basically we only want it to accept tension. We don't want it to carry any compression. That compression should be carried by other elements. Now, if I just go ahead and run this analysis, first of all, just look at the loading here. We're only concerned with a few of the loads. The dead loads, which are 3 kPa on the floors, and the live loads, which are 5 kPa on the floors. And we have a load combination. Actually, I don't think we have one yet, but that's not important. We'll get to that later on. And in this model here, you can see that we do have some bracing that's modeled with this section that you can see here, the blue section, the light blue section, the HS 168 by 6.4. And if we look at the element types that we're using, we're truss element types for these bracing elements. So basically that just tells S-frame that these bracing elements will only support axial loads. They don't have any shear or moment carrying capacities. Whereas the other elements are beam elements, which do have the ability to carry moments and shear, as well as axial loads. So we're going to go ahead and run an analysis. We're going to run a linear static analysis first. And I'm interested in seeing, well, how are those braces doing in terms of carrying the different types of loads that I have? So I can pretty much look at either the live or dead load cases. The magnitudes are the same, it's just, or the different, but the orientations are the same. And I can see things like the deflections. We can get an idea for how things are deflecting, but I'm really interested in the axial forces. More specifically, I'm interested in the axial forces in my bracing, which I already have a group folder for. And I can see here, again, it's showing it kind of scaling it up a little bit unusually, so I'll just change my scale factor. We can see here that we have axial forces, and they all happen to be negative. Now in S-frame, a negative axial force is indicative of compression. So these aren't actually behaving the way we want them to right now. We would want them to basically not carry any loads if they are in compression. So how would we be able to address this? Well, we could consider just deleting these braces if we know that these load scenarios are causing compression only in them. But that's kind of a nearsighted solution because let's say we add some lateral loads later on. That will completely change the load path, and whether or not these braces are in compression or tension will totally depend on the magnitudes and the orientation of those loads. We could also say, well, why don't we just inactivate the ones that are in compression, reanalyze, and go from there? Well, again, that's going to change the load path that we have, and it will be very difficult to maintain that approach for a complex model with lots of loading scenarios. So what we can do instead is we can say, rather than using this truss element type, let me use a tension-only member type. So with the tension-only member type, I'm just going to left-click and drag to apply it. It's this light blue color. When it's in tension, it will behave the exact same way as a truss in tension would normally behave. It will only support axial loads, but specifically it will only support tension loads. So if it's in compression, and during the analysis it found that, okay, there's compressive loads in this member, then it's going to say, well, then you have no stiffness at all. So let's try analyzing this again, but with these tension-only members. I'll click Analyze, and I'm going to run a linear static analysis. And here, by design, I did this on purpose, just in case you guys are curious, we're getting an FYI. This is a diagnostic message here, and we can see here that says tension-only truss converted to truss. So basically, it's identified that we have a tension-only member, but it's found that because we're running a linear analysis where the solver doesn't have the ability to tell before the end of the analysis whether a member is in compression or tension and inactivate it, it's just going to assume it's a truss, which is always going to have the ability to support tension and compression. We need to run a nonlinear incremental analysis in order to account for this tension-only behavior. So let's try analyzing this again, because if we look at the axial loads, we'll see that, again, they're all in compression. Now let's try analyzing this one again, but this time I'm going to do a nonlinear static analysis with the default convergence parameters, and I'll click OK. And now we're actually getting some issues with our analysis. We're getting some issues with it not converging. Basically, what it's found is when we remove those compression or those tension-only members, because they were all in compression, they're all going to be ignored by the solver. We had some issues with stability. And this is one of the downsides of going with a nonlinear analysis, is that it's a little bit unforgiving with unrealistic loading scenarios. We have to consider the fact that having purely axial or gravity loads isn't really a realistic scenario in the real world. We would probably have some sort of imperfections in the model, maybe some lack of plumbness or some sort of geometric imperfections that would be inducing lateral loads. And so we're not able to look at these results because with just those gravity loads, these are found to be in compression and they're actually required for stability in the model. So what I'm going to do is I'm going to just induce some lateral loads using notional loads. I'll go to the Edit Load Combination dialog. And what I'm going to do is just say, let's create a load combination of the dead and live. I'm going to create a notional load factor of 0.005, so 0.5%. And my load combination is just going to contain those two load cases, the dead load case and the live load case. I'm going to factor them with 1 each. So what that means here with those notional load factors is, if I take the combination of dead and live loads and I take the total gravity reaction, so the force that my foundations are pushing up on my structure with, I can then multiply that by 0.5% and apply it in the lateral direction in X as well as in Y. So I'll click OK. Now I'm going to rerun this analysis. I'll just say, let's just run our load combinations only. And it seems like I may have made a mistake along the way. Again, one of the realities of these live demos, which I experienced last time as well, is that we do make some mistakes, but I think I have a model that's working here, so just give me a minute to open that one up. Probably skip the important part of the demonstration. So here I've got the same model, but again, with a few additions that I've made, I'm just going to change these bracings to be tension only. And hopefully with this change here, we'll be able to analyze this again for a nonlinear static analysis and get things working the way we intended. So again, here we can see that it did analyze. We did have some issues with our analysis for one of the load scenarios that just had gravity loads only that I didn't update. But now I'm going to look at the results for my dead and live load case. That was the one that just had the gravity load. So that one actually did have some stability issues because it did rely on these tension-only bracings to have some compression on them to be stable. So I won't look into that one, but I'm going to look into the dead and wind load case or load combination, and specifically focusing on the tension-only bracing that I've defined. And I just want to see here with the axial load diagrams, what sort of magnitudes I'm getting for these axial loads. So you can see in one direction on each side here, we're getting some tension, about 11 or 12 kilonewtons of tension. But if we look at the bracing in the other direction, we have 0 kilonewtons. So we have no negative axial loads, indicative of no compression in these elements. So hopefully I didn't confuse you guys too much with that, me stumbling through the first exercise. This one was the model I should have been working on. But you'll get an idea as you use this in practice. So that brings me to the end of today's session here with what we discussed. I think I have a few upcoming event notifications I wanted to just make you aware of before we open up the floor for any last minute questions. Oh, I forgot to put that there. So again, what we have coming up later in this month, we have actually another presentation for the Steel Center on stage construction analysis. So basically looking at the construction sequence as we go through an analysis and a design process. We also have some training next week on finite element analysis applications, which I think a few of you guys have already registered for. I'm not sure if the registration is still open. We are getting pretty close since we won't be open over the weekend. But we do have an upcoming training course on nonlinear and P-Delta analysis as well. That will be the last week of September. And if you're curious, we will be sending out email notifications about these training courses, but you can also register on our website. That's sframe.com, so www.s-frame.com. And if you have any questions, by all means, get in touch. I did make a recording of this session, so for those of you that maybe didn't log in right at the very beginning, we do have that information available. I'll send it off to Professor Driver at the end. So if there are any questions, I'm happy to stay on. Otherwise, thank you all for your time, and we'll be in touch.
Awesome. Thank you so much, Matt. You could just flip to the last slide over there. Thanks. We really appreciate this. This was a really good presentation. Thank you, everyone who attended. Once again, we had Matthew Sawyer, Senior Application Engineer with S-Frame, on the P-Delta and Nonlinear Analysis. I'd like to encourage everyone here to take a look at next week's presentation. We have a presentation about idea statica. So if you're interested in learning about component-based finite element method with connections, please join and invite your friends.